Thank you. We are welcome back. So, continuing on time series, in the morning we looked at the theory behind autocorrelation, partial autocorrelation, and how it works on time series. So, moving on to further aspects. As a recap, time series data are made up of records or data points collected over a certain time range, for which analysis of data sets with a timestamp index can be carried out. That is, it is associated with time. Data was collected over time and usually at regular time points, daily data or monthly data or weekly data. And the some data you have to aggregate to have better analysis, but aggregating data to yearly data is usually not advised because the data points will be reduced, and so some hidden patterns may not be properly observed. So depending on the goal of your analysis, disease data are usually taken as monthly data. But like I was discussing with someone, and their type of data, is like a data from storage, harvest, that there are harvest periods where you get the data. So the important thing is that if there's a regular collection of that data according to the timestamp of the system you are studying. So analyzed time series data can be used to forecast or predict other data points, which could be of great importance in making early decisions for improved health outcomes, for improved actions on various aspects. It could be on finance, it could be on food, it could be on many aspects that SDG really promotes sustainable development growth. Whatever aspect of data you are getting, is good to develop a consistent record, and then if possible build a data body, or let's say a good data system where you keep getting regular information so that over time you can observe, and from what you observe you carry out an analysis and pre-analysis like time series to be able to make early decisions. So some data are univariate or multivariate. Univariate data are when you are considering just one variable. Multivariate data is when you involve other variables. Like you may be doing disease data, and then you want to also consider the rainfall over that same period of time. So you are dealing with two variables. So here I just have an example of a time series data where the period column is the timestamp, and the second column are the cases data, and the third column are LLIN data. So depending on the kind of analysis you want to carry out, we determine whether to go for univariate or multivariate. But ARMA time series usually is univariate. We pick just, for example, we pick just the malaria cases with the timestamp, or if we are interested in LIN distribution or coverage, then we go with the second column. And if you observe from the plot displayed, there are some missing data in the LLIM column I have there. So not every data comes perfect. There are a lot of basic statistics you need to do on your data to be able to achieve good analysis. So the first thing you do when you get the data is to check the data to see what it looks like. You don't just go straight into analysis. So if you need to fill in missing values, if you need to carry out some analysis of where you have to normalize so that the variance in the data distribution won't be much, which helps for better observing of the patterns and for better prediction or forecast. So some time series analysis can be, for example, we have the ARMA. The ARMA, which I said is mostly univariant. Then we have the wavelet models, which can handle multivariants, like when you want to do correlation analysis and all that. So depending on the level of analysis you are carrying out, the time series modeling has long and rich history in epidemiological pursuits, like a study that studied the dynamics of influenza and endemics in space and time, where disease counts were considered to follow multivariate autoregression process. ARIMA model lies mainly on historical data without considering external factors. That's why I said it's more of a multivariate data, and these factors might be factors influencing even the multivariate data you are working with. So it's usually good for ARIMA is usually good for early data analysis, more like a pre-analysis of your data. Mathematical modeling goes deeper to look at the dynamics of the system you are studying. It could be disease, it could be whatever system you are studying, not limited to disease, and then considering other variables that could have influenced the cases or counts that you observed over time. So time series forecasting or prediction can also be done with machine learning models, which learns the relationship between input features and output, which can then be used to make predictions on new or unseen data. Now, to carry out forecasts, like I said, first of all, you get your data, then you carry out some data preprocessing, where you have to clean the data and prepare it for your analysis. Then we have the model selection. In this case, this time we'll be looking at ARIMA. Okay, so because we want to do a univariate analysis, we just want to consider a variable, and then it's good practice now to always train your data, then test it. When you've selected the model, you split your data into certain percentage, could be 70-30, it could be 80-20, and there are other methods of data splitting, so that the model you selected will be trained on the higher percentage, and then you carry out evaluation. When you've selected the model, the trained model, when the trained model has been trained, use it to forecast within the range of the test data you set aside, and compare the results to see, using tools like root mean square error, to see the error percentage between the actual data, the actual test data, and then the one you forecasted. And then after that, you're able to still further select or decide on the goodness of the model you've selected, and you carry out final prediction for informed decision. So we want to briefly go through our R. We'll be using just that air passenger data, which has already been cleaned. So not all data comes perfect. So you have to run some basic statistics like we were taught in previous classes, where you do the summary of your data to see the mean, the variance, and if the maximum value is so different from the mean value, at times you need to reconsider applying transformations to your data. You can apply square root data. You can apply square root transformation. You can apply log transformation. But when you have a data that has so many zero values, log transform wouldn't be a good decision, because when you log transform 0, you get, infinity. So in such a case, you have to open your data, look at the data, what is in the data, see how it is. Are there missing values? Are there inconsistencies? Are there zero values that make no sense? But no data is a waste. It just depends on how you clean it and try to bring out good information from it. Then from there, you can now recommend, based on your forecast and predictions, on better ways that should be improved on in getting data, and how to ensure that we're able to get better information from our data system. So in the morning, we've already run our air passenger data. I sent a data to the platform. I don't know if we downloaded it. Just wanted to use that to show us an example of what can be found in a data. So if you actually downloaded it, try opening it. If you open it, you discover that there are a lot of 0 points there. So such a data was sent on the platform. So such a data, you discover that even if you are going to use it, you have to do a lot of cleaning on it. So when you have your data, look at the data and try to study the nature of the data. Let me see if I can open it. Yellow, yes, yellow. Discover that there are a lot of zero values there. So one might want to discard it, but data is value, no matter how little. So we try to see what can be done to get the information available, and then how to improve on the data. Okay, I can't find the data here, but let's continue. So going on with our data tree, we have viewed it in the morning, and we can see that this data was well collected, no missing data, everything is going on fine. I could try to still do the summary statistics on it. Here you can see that the maximum value in the data is 622. The mean and the median are within a good range, and the first quarter and the third quarter are not too variant from each other. So, but when, for example, let me see if I can still get that data I sent, then we'll look at the summary statistics. Now, before you can view a data, you have to save it in the file, in the folder where all your work is, or where your R code is, so that your R will be able to trace it. Okay, so just as a revision, if this is where the data is, you have to copy the paths to can copy the address by right clicking on this search button here, or if your folder page has copy paths, you can easily copy paths. So some don't show copy paths, so you can always come to this search button, right click and copy or copy address. Then you come to your working directory and you paste it there. Okay, so for R, the backward slash won't work, so you have to either double the backward slash or use the forward slash. So I prefer to double it. So if you succeed in running that line with no error, then definitely you'll be able to call out the data set that we want to try out. So I want to call the data, I call it fever, and I say read.csv, then the name of the file. To verify, you go back to the folder and check the actual name, and be careful that the cases are right. If it's lowercase, then you must use lowercase in R. So yes. Okay, so I've been able to read it in without any error. So if you have any error, then there must be an issue in your part or in the case when you are typing the data. Okay, so we just want to check. Let's check what's in this data. We can view, or we can just run it as fever. So these are the contents there. You can see a lot of zeros in the data. So for this kind of data, if at all you want to do any transformation, doing log wouldn't be a good idea. Okay, so let's see the summary statistics of that data. So this summary statistics give us the summary for all the columns. But if you want it specifically for the case variable in the data, you say fever dollar, you select the variable you want to look at. You click on summary. So you have the summary. So you can see that the maximum is so far from the third quartile, the first quartile, the mean and the median. So you know that this data, you still need to do some extra cleaning. But basically, since there's no missing value there, the only thing you can do is to normalize it, or you transform it using square root transform, since log transform is not an option because of the number of zeros we have there. Okay, so that's just a little on preparing your data. Then now we continue with our data tree, which is air passenger. In the morning we did the we put it in time series format. and we carried out the ACF and PACF test on it, and we also check for stationarities. So it needed no transformation. It needed no differencing. So D is still 1. So now we want to, since we want to do our ARMA, okay. We did this in the morning. The first one, okay. Okay, for the first one, you can just snap it. Just a brief hint into summary, into some things that can guide your decisions on how to start analyzing your data. Can we move on? We may have to move on. If you can snap it, and okay. So when you are reading your data from your system, which is what you obviously always do, because when you get your data, you have to save it and then you upload it to R. So you must get the parts of the file where you saved it right. And then when you want to read it, you make sure you are using the right file name. Can we go? Thank you. So from our ARMA PDQ, at a first glance, okay. Yeah. Now this is just a comment. So if you want to get your ARMA parameters manually, we can say that our P is now equal to 0 because we didn't do it. Sorry, our D will be equal to 0 because we didn't do any differencing. Our P, from what we have in this plot, we can't really say what our P is because there's no point where the significance drops to the cutoff threshold. So a strongly correlated data, which is a strongly correlated data decays slowly. You can see that this data really doesn't want to, the autocorrelation is not decaying to the cutoff. Why a very stationary data would decay faster. But in this data, the cutoff point is this blue line. Within this blue line threshold, when we have a cutoff in the significance of the autocorrelation, we could pick a value for our observed autocorrelation. And for the PACF also, yes, we have from 0, there's really no significant value. So we can leave that as 0. So usually the PACF would, what we read from the significance values will be put for the Q, while the ACF will be used for the ACF will be used for the P and the PACF will be used for the Q. So assuming we are following this, because there is no cutoff here, we could just assume a big value here. Let's say 9. But the smaller the value, the less the complex your model. So we can say 5. But it's usually good also to use autocorrelation, ARMA, which will help you select the best model that can analyze your data. So from manual picking of the parameters, this is what we have. We want to assume this. We have from, this is 0, we have 1, 2, if you are seeing my mouse, 3, 4. Can you see the mouse? 1, 2, 3, 4, 5, 6, 7. At 7, it came down. Then again, maintain some station, although not coming to the cutoff. So let's say 7 here. But this is not the best ARMA. This is just an initial value of the ARMA. Okay. 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 Welcome. All right. So these are the significant autocorrelation observed in the data. And up to the end, we cannot see the autocorrelation decaying to within the cutoff threshold. So the cutoff threshold is this dashed line we see here, that according to the properties of autocorrelation we did in the morning, that when we take the absolute value of the autocorrelation or of the variance, we want a situation where it's between 0 and 1. But here it is not coming down to that. So, but for manual estimation of your parameters, we can count to a point where we see it's decreasing. But we know that that may not be the best model for it. But for the initial, to determine your initial ARMA values, before you now carry out other model estimation to now select the best model. Okay, so this is 0. The first the first line usually is 0, correlation with itself. Then we can now see the other moving averages. So we have 1, 2, 3, 4, 5, 6. I think at 7 it's a bit station. So we can just, for an initial value, we can set 7. So that's why we have 7. Then for the moving average, we get it from the PACF, which is already within or below the cutoff right from the beginning. So it's 0. Okay, so we go ahead to also want to see if there's seasonality in this data. Now we have done data decomposition. So just to check again, I decided to save the data in a name called my data. Then I carry out decomposition using the STL decomposition, which will show me the level of impact each component in the data has on the observed data. So we can see this data is the observed data. The seasonal pattern is here, the trend, then the remainder. And the trend seems to have more effect on the data than seasonality or remainder. Okay, so there's no point putting seasonality in this data. Therefore, we are going to just stick with ARMA instead of SARIMA, which is seasonal ARMA. All right, so on this line 30, we set the data to be in time series format. You remember that the data started in 1949. Okay, so we run it. Then to be able to split the data for better analysis, to be able to split the data for better analysis, we in line 32 do a data splitting of training data to be 30, to be 70, and testing data to be 30, like I explained earlier. So the total train size is the length of total data, which is n. So the train size, the training data size, is the floor or all data points within the 70% of the data. So we create a window for it, for the training sets, and then we create a window for the test sets. So we split the data into two groups. So when we are training data, it will be working on the training part, and when we are testing, we'll be using the testing part. Can we move up? So you don't need to copy all the comments there. If they are too long, you can abbreviate your own comments. Up. And there's no time. My time is almost up, and we've not gone to forecasting. So just snap it if you can. Okay. So you have done this morning. That's why I scrolled up. So is this point okay? Go up, up, up. Is this okay? So we did this part in the morning. Can we go down now? All right. Thank you. Okay, so, okay, let me put a line so you know the continuation. So here, we looked at the seasonal part, be sure of the kind of model we want to use, and now we know we are just using ARMA. So have we taken that? All right. Just snap it, please. Then moving on, we carry out the split and splitting of the data to 70-30 ratio. Okay, so after doing that, on line 38, you can see the, yes. We did not what? Yes. Yes. Yes, sir. I'm almost. Okay. So we'll send the code to the platform. Okay. So you so the ARMA part now, we use autocorrelation, auto ARMA, to select the best model, and the seasonal part we set it at false, since our data does not have all that. We can also delete all these stepwise and approximate, but it comes with the format we set to false. Okay, so if we run now, we've not run line 32. So this is where we do the split. So for you to train the data now, we are developing the model based on the train set, train TS, as you can see here. Okay. And we saved the model that will be chosen in a place called case fit. Sorry. So after doing that, you can check the model parameters that was selected, and you see that if we scroll up here, we have the best model that was selected was 0, 1, 5. You see that it's not too far from what we observed manually. We observed 0, 0, 7. But the auto-RMA is making us know, instead of making it more complex using higher values on the Q, we just do a one-step difference here for the D. That's why we have 1 there. So this is a best model for this data. And then we have some other parameters down here that were used to select the best data. These are parameters that come with ARMA to be able to for deciding which model to finally settle with. Okay, so when displaying your results, the selected model, which is this ARMA 015, would also be displayed with all these values that were used to choose. Why did we choose, or why was this model selected as the best? One thing is that the AIC, ICAMMDA information criteria, is a criteria in statistics that is used to check best model. So the lower the ICAMMDA information criteria, the best or the better the model. So the auto-RMA has tested various parameters of the ARMA, like the PDQ. Maybe they tried 0, 0, 5, they tried 0, 0, 7 like we chose initially. They must have tried different variables within those three, and then saw that this final selected one, 015, had the lowest AIC, which is 888.33. And then we can now go ahead to forecast data based on the test data. We want to use this model to carry out a forecast and see if the values it gives us is close to what the original data has for those data points. So running line 44, we carry out the forecast, and the length should be the length of the test data. And then to view the values that have been forecasted, you click on forecast values. So you can see the values that were forecasted. The trained data was from 1949, and 70% stopped at April 1956. So here we now forecasted from where the test data point starts, from 1957, May 1957, yeah, to the last point, which is 1960. So you can now look at this first column, points forecast, is the mean value, the best fit line or relation to the values that were forecasted. Then we have the low confidence interval of 80%. We have the high of 80%, and then the low of 95% and the high of 95%. So what it's trying to say is, between the border of 80%, 95% confidence interval, possible values are forecasted in between. So if you see the point forecast, see that the range is in between the low and high of the confidence intervals. So let's just look at this May 1957, June 1957, July 1957. Then if we can, I'll go back to the air data and run it. I want to view those points in the original data and see if the value is close to what we're giving here. So you can see the last line here. Okay, it's not showing very well. But you can see the 7 there. That's 1957. So in 1957 January we have 315, then February 301, March 356. Now let's go back to the one we forecast. Let's just check January, February, no, sorry. The forecast began from May. So let's see May, January, February, March, April, May. So May is 355, 422, and 465. So we've also up here, let's check what was predicted or forecasted. So here we have for May 350, 346, 319. It's within, not too far from that, because if you see the low and the high, the actual data, the actual test data is still in the 95 percentage. It still falls there. You can see for June 1957 in the original data we had 422, while here the 95 confidence level of June is having 407. So relatively it's close, it's giving a closer prediction to the original data. So to some extent we can go ahead with this model, and you know, for every model there will be some level of percentage error. That's why where we got the model parameters, you can see the root mean square error, the mean average error, the mean percentage error, and these are all error parameters that can be used to test to see how far a model is from the data. So you fit your model to data. Okay, so having verified our data, we could decide to let's just print out the root mean square value. What's percentage error? We have a percentage error of 117, and we had I think 1957 June was 36 something. So by the time we add 117, we are getting close to 422 of the original data. So it's just a way to verify your model and see how well it aligns with the data. Having done that, now we can now use that model to we train the model to the full data. Now remember, we trained it to just the training part. So now we want to make forecast, so we train it to the full data. Here we can see that X now is now data underscore 4, which is the full data. Initially when we ran the autocorrelation in line 38, we trained it to the training data, train underscore TS. But here now we are taking the full data to run it, and we fix in the order of the ARMA. Now that we know the model we are dealing with, we run it, we fit it. Then in the forecast here, we want to do a forecast of 2 years, which is 24 months. The other forecast we did a forecast according to the length of the test set, because we wanted to carry out comparison. But here now we want to actually forecast for the next 2 years. So we can go ahead and run that, and you can as well view what is forecasted. So you can see it forecasted up to December 1962. That's 2 years ahead. You can view the data if you want. So we have the point mean forecast, we have the low, the high of 80% confidence interval and 95% confidence interval. And it's a good thing to go through the values given. You can see that they are all positive values depending on what you are analyzing. Like our original data were mostly positive values. So if we get a negative value here, we could there could be some questions, further questions or further analysis to carry out to test. Like what we have, what we call residual check. You check the residual to see if it has a role to play in the variance or in the in what is observed from the results. Okay, so now line 54 is just a way to save the values that you forecasted, because sometimes if you don't save these things in a CSV or somewhere where you can refer back to it, you may have to keep rerunning your code anytime you need the value. So in line 54, I created a data frame where I called in all the parameters in my results. So you can see the first one here is the forecast dollar mean, which is this first line. The second is the lower confidence interval of 80. We have the one for the higher of 80, lower of 95, which is 2, and higher 2. You will get the code. Okay. All right. So yes. So now then you need the package called reads R to be able to actually save or write your values into a spreadsheet. So I call the package and then I do this. So because everything you are running, you are in a particular path, you set a working directory. So this file will be saved in that working directory. If you go to that file, you should find it there. All right. So now the next line is to plot the forecast. And as we've been doing plotting, so to plot the forecast here, we just say plot forecast case fits, and then the forecast of 2 years. So if I run this line, you can see the forecasted time series. There, so two years ahead was forecasted, and then you can also put the legend. So I don't know why the legend, so you can adjust the boundaries of the legend. So let's see. Okay, so okay, so I think we may have to stop at this point. Thank you very much.